Hello, hello, hello. I can see. Adetola, how are you? How are you, Salman? How are you, PH? How are you, Olivier? How are you, Cesario Oñada? How are you? Okay. How are you, Ray? How are you, Marlon? I hope you all can hear me okay. It's a pleasure. It's a pleasure to run this session with you. As you can see, my voice is operating right now on a sigma level around 2 or 3, but I am almost 100%. Yes, I feel that in a few days I'll be 100%. Yes, the temperature is changing quite a lot here in Brazil. Sometimes in one single day you can have all 4 seasons, yeah, and it creates some challenges for us, yeah. But everything is gonna be all right. Yes. How are you guys doing on a scale from 0 to 10? Please let me know on a scale from 0 to 10. How are you guys doing? Yeah. And today we'll be deep diving here. Take a look. That will be our best friend. Okay, our best friend. Just 1 second. Yeah. Wonderful. William, Gladys, Jeffrey, Jeremy, yeah. And now let me know the quality of my audio. The volume. How is my audio on a scale from 0 to 10? Please let me know. Oh, that's great, PH. I'm glad to know that. Yeah. Vindra, recently we had a wave in Asia, So yes, so I decided to run this session on a more east friendly time. Yeah, east friendly time. So I know it's not night for you guys in Africa. Yeah, and we'll be kind of alternating or maybe running multiple sessions with the different options. Let's see how things go. Yeah, that's great. Wow, Trinidad and Tobago. Right now it's super early, right? What time is it for you guys in Trinidad and Tobago? Let's see here. Oh no, it's not. It's not that early. It's 8 a.m. I thought it was like 5 a.m. or 4 a.m. Yes, yeah, 8 a.m. So it's okay. It's okay. Perfect. So let's go ahead. Let's go ahead. Please let me know here. Let me know here. Yeah, and by the way, let me just collect this data. Type here, what time is it for you now? For all of you guys. Type here for me. What time is it for you now? So we have 1 p.m., we have 8 a.m., we have noon, we have 8 p.m. My Asian friends, 8 p.m. again. Then we have 8 a.m., 7 a.m., 3 p.m., 2 p.m., 5 p.m. It's a global audience. It's a global audience, right? Wonderful. Wonderful. So let's go ahead. And now I need to measure again one thing. Control charts. Type here for me, where are you? One means I have never heard about control chart. 2 means I've heard, but I don't know what's that. 3 means I've heard, I know what's that. And 4 means I've heard, I know what's that, and I have applied. So again, I have no clue about control charts. 1. 2. I've just heard, but I don't know what's that. 3. I've heard and I know what's that. And 4. I have applied. I had a chance to apply. Two, 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 one, two, two, one, one, three, four, one, one, two, two. Okay. Okay. So that helps me on calibrating how to present this beautiful technique. Yeah, and it's impossible to talk about control charts without talking about Walter Shuhert. So please keep in mind this name, Walter Shuhert. Okay, take a look in his picture. Yeah, that's the famous Walter Shuhert. If you want to, if you want to, if you want to do your research, take a look here on his picture. That's the man. That's the man. When he was really young. Yeah, he proposed control chart 100 years ago. Yes, in fact, he's the father of statistical process control. Yeah, he's not physically among us anymore. Yes, but his work is very much alive. Very much alive. Yeah, Walter Shuhert. And just for you guys to have an idea of the importance of Shuhert for the quality management topic in general, uh, probably the most important quality guru of all times is Edwards Deming. Yeah, hand in hand with Joseph Juran. Yeah, Joseph Juran and Edwards Deming. But many authors put Edwards Deming in first place. Yeah, because of his contribution to the continuous improvement culture in Japan. Yeah, this is quite interesting. Like an American to have in Japan an award with his name. Yeah, knowing that we have absolutely different cultures. Yeah, if we consider East and West. Yeah, this is quite interesting. And he has an award with his name in Japan. And his 14 points, Edwards Deming, with his 14 points, definitely changed the way world, yeah, managed. There is a quality management before Deming and a quality management after Deming, post Deming. Yes. On top of that, apparently Joseph Juran was very good in terms of management in general, but not a kind of very expert in terms of technical topics, differently from Edwards Deming. Deming was very powerful in both areas, in the, let's say, in the soft area, management in general, the cultural, the philosophy, the equality philosophy aspect, but he was a true guru in technical terms too. Yeah, Deming was a statistician. He was the master of the master in terms of statistics. Yeah, and Deming, every time that someone claimed that the PDCA cycle was Deming cycle, Deming was very clear in stating that no, this is not mine. This is not my work. This is Walter Shuhert's work. Yeah, and Deming was always reinforcing, highlighting the work proposed by Shuhert. Yeah, so again, the contribution from Shuhert was recognized and highlighted by Edwards Deming. Yeah, Deming definitely had Shuhert as a hero, Yeah, so that's the kind of contribution of, just to have a piece of information in terms of contribution from Shuhert. Yes, and once again, he's the father of statistical process control. So in very simple words, Shuhert was the very first person that raised his hand and said, hey, we don't need, for example, to inspect 100% of the parts. Yeah, we don't need. We can work with sample. Yeah, with a sample. We can apply the concept of sampling. And sample is always cheaper, more controllable, faster to get. Yeah. Yesterday I went I had to collect some blood, for a blood exam, for a blood test, and I was thinking about the beauty of inferential statistics. With just a sample of my blood, yeah, the laboratory was able to reach the very same conclusions that they would reach if they analyzed my 100% of my blood, right? That's beautiful. This is inferential statistics. This is a kind of SPC, statistical process control. I am fortunate enough to be a person that does not need to take this kind of measurement every day, yeah? But you know that it is possible depending on the exam, yeah? Especially there is one kind of exam when you have there is a hypothesis about diabetes, yeah, that you need to collect during a day every hour. Yes, every hour. This is pure SPC, statistical process control. You are trying to understand the system, the process, based on different samples over time, right? Over time, yeah. And then one of the elements of statistical process control is control charts, yeah. So a control chart is a type of graph that is very much powerful and very much used in Lean Six Sigma, yeah. Mainly, or at least, in 2 out of the 5 steps in the make. Yeah, we have define, measure, analyze, improve, and control. In the Lean Six Sigma project, you will be, for sure, using control charts at least in measure phase and in control phase. Measure phase to present your baseline, yeah. How is your process? What's the size of the problem that you are trying to solve? Yeah. And at the end of your project, when you compare before and after, the famous before and after comparison. Yeah. The famous before and after comparison. Is it make sense in so far? And then we'll be deep diving in these, basically in these two types of control charts, yeah, or these 2 control chart models, yeah. Is it okay? Wonderful. So let's go there. If you are new to Lean Six Sigma, not a problem. Don't feel pressured, to fully understand exactly what I am doing here on Minitab. At this point, you do not even need to know which software is this. You don't need, okay? So please, now concentrate in understanding the concepts and principles. Yeah, the concepts and principles. Yeah. So I want to present the following scenario. Please imagine a production line of something that I have never talked about this before. Take a look here. Who knows what is this? Now I'm gonna see who is my at least a white belt. If you are at least a Lean Six Sigma white belt certified by me, yeah, you know what's that. Take a look here. What's the name of this beauty here? And I hope you are not hungry. I hope you are not hungry. What's the name of this beauty here? Yee-hoo! Yee-haw! What's the name of this beauty here? Oh my god. Yeah, cheese bread. So I want you to imagine a production line, of cheese breads. So many cheese breads being produced. I don't know, maybe 100 per hour. 100 per hour. Yeah? So 100 cheese breads per hour. And I want to check how crispy they are. Yeah, how crispy they are. And for sure there is a way to measure that, but here just to simplify, in fact we will need two important simplifications here. Let's assume that we can measure this as a continuous data, continuous data, and it must be anywhere from 5 to 15, and I would love to have as close as possible to 10, yes, to 10, from 5 to 15, yeah. And if it is below 5, we have a problem. If it is too crispy, above 15, this is a problem as well, yeah. One important thing to reinforce is that control chart is a tool focused on evaluating stability, process stability. So, by the book, by concept, we don't talk about specification limits, client limits when we have a conversation about control charts, okay? But just for you to have an idea in terms of how good it is a cheese bread, yeah. In terms of crocancy, how crispy it is, yeah. So cheese bread. That's the name of our variable. Yeah, how crispy it is my cheese bread. Yeah. And then I went there I went there at 8 a.m. Yeah. And then I took one sample, just one sample. Yeah. And it was 11 in terms of, yeah, how crispy it is. Then at 9 a.m. we took another one and it was a 10. Then at 10 a.m. we took another one and it was a 9. Yeah? And then we had a chance to collect 10 samples. Let's make it super simple. Yeah, super simple. And then it was a 10. Then we got a 10.5. Then a 9.5. Then 10. Then 11. Then 10 again. And then 9. Okay? One very important thing to highlight. You do not want to use a control chart if these data points here represent population. This is one of the most common mistakes you will find among people that use control charts. Control chart is a tool, a graphical tool, you can consider as a graphical tool, that is part of a technique, a group of tools named SPC, Statistical Process Control. So, Walter Shuhert proposed a way for you to control, to manage your process in a statistical way. So it is expected that you collect a sample. So I don't know, from 7 to 8 a.m., the cheese bread production line, manufactured, produced 100 cheese breads, and then I took one. And then from 8 to 9, another 100, and then I took one. And then from 9 to 10, another 100, and then I took one, a sample, a fragment, a portion of the production. Is it clear? Is it clear? This is simple, but it is so important. This is vital, and I have to tell you, many belts make the mistake of plotting a control chart with population data. And again, it should not be applied. If this data represents population data, I mean, there is no reason to talk about statistical process control. No, and then you just go ahead and plot for example, a time series plot. You can just go ahead and plot something like that. And then you have each data point here. You have a flavor in terms of variation, a flavor in terms of central tendency, in terms of process centralization, and that's it. But see that with control charts, it's different. With control charts, what I am proposing is something different. What Shuhert is proposing is something different. And once again, please don't worry about the technicalities, all the Minitab technicalities, not at this point. Yeah, if at some point you have interest in becoming a certified green belt, then you have a chance to deep dive in all these Minitab technicalities. Yeah. Wonderful. So see, what's the main difference between this guy here, between this guy here and this guy here? And please focus only on this piece here, yeah, at the top. Please, what's the main difference between this graph here and this graph here? What's the main difference? Yeah, what's the main difference? What can you see, differently? What can you see differently? Or let me make this even. Yes, Cesario. Yes, Cesario. So I did not need to make it simpler. Yeah? Yes, Cesario. So see that we have control limits. We have control limits. And I think it's cutting a little bit. Let me see if I can adjust here real time so you guys can see the control limits. Now it's better, right? Now it's better. Yeah, is it okay? I don't know if there is a red line here that kind of annoy. Let me see. No, I think we are good, right? Yeah, we are good. Perfect, perfect, perfect. So see, we do have control limits. And what's the right interpretation of these control limits? Let me zoom it for you. Yeah, what is the right interpretation? Can you guys see, please? Oops. Type yes for me if you can see that in one of the main differences between a control chart and a simple time series graph is that we have these red lines. Yeah, these red lines. Please type yes here if you understood that. Yeah. And what is the main objective of control limits? Well, if the name of the tool is control chart, very likely control limits, I mean the name control limit sounds important, right? For a control chart. Sounds important. Because once again, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, just I want to check if you guys are here with me or not. These 10 data points, very likely came from a population by which size? What was very likely with the numbers that I was here, yeah, presenting to you, the production numbers, you know? So 10 data points came from, 10 data points, the sample came from which population? Very likely. Which population? See, here we are not talking about acceptable crisp value, how crispy it is. Remember, control chart, we are talking about process stability only. We are just checking if process is stable or not. Yeah, for specification limits, we do have another technique named capability analysis. Yeah. But these 10 data points came from like 100 cheese breads per hour. So if I'm talking about 10 hours here, very likely I'm talking about 1,000 cheese breads. Yes, 1,000 cheese breads. So what was the highest value here? The highest value, the max value was, can you guys see? 11. And the lowest value was here 9. Yeah, so from 11 to 9. Yes, from 11 to 9. But with the technique proposed by Shuhert, he is saying that even knowing that in your sample you got the lowest value as 9 and the highest value as 11, from the data that you brought me so far, please expect to have in your process cheese breads that will be crispy in a level from 7.636 to 12.364. Anywhere from 7.636 to 12.364. So I need to know if you understood that. This is so important. Maybe one of the most important topics of today's session. Control chart is a tool as part of a technique named statistical process control, where we'll be necessarily working with sampling. So we'll have samples, and based on this sample we'll be able to estimate process variation. We'll be able to estimate process variation. Yeah, process variation. Yeah, let me know, Paul, if that was helpful. Yeah, process variation. Marcelo, are you sure that the next data point will fall between 7.636 to 12.364? Are you 100% sure? No, I am not 100% sure. And if you want to take note, there is a number. Yeah, it's 99.73%. Yeah, 99.73%. No, these control limits, I'll be talking about them. I'll be explaining. Yeah, I'll be explaining how do you calculate. They are not defined, Vindra. Control limits are not defined. They are calculated. Yeah, calculated. And I'll be giving at least a flavor of that. Yeah. So it estimates that if we measured all the population, the variable would fall within 95% confidence interval. Very good question, John. Very good question. In fact, it's more than 95%. In this case, it's 99.73%, because you have 3 standard deviations from one side, 3 to another. This is very simple. You guys can even Google that. If you, let me see if I am lucky enough to show you guys something here. Yeah, if you guys want to understand why 99.73, you can even Google that. If you put normal probability distribution, and you can even go to image, very likely. See, I was lucky enough. See, even if you Google that. Oh, no, not chat now. See, I don't know, I think it's too small, right? I hope you guys can see. Stop seeing this ad. Uh, this is the normal probability distribution, and then when you have one standard deviation to one side, one standard deviation to another side, you are approaching around 68%. Yeah, of the, let's say, using a simple word, you are approaching 68% of the possible values. You know, two standard. So if I go further and I approach two standard deviations to one side, two standard deviations to another side, we are covering around 95%. But if I change now to three standard deviations to one side and three to another, we are approaching 99.73%. Yeah, so that's why it's more than 95%, right? Yeah, it's more. By the way, the 95% normally is associated to a z of 1.96. Just out of curiosity, now it's kind of technical. So why 1.96? Because it's not exactly 2, because 2 it's a little bit more than 95%, right? So if you want to reach 95% sharp, then you should go a little bit less than 2 standard deviations, right? That's why there is the famous 1.96. Z equals to 1.96. It's very, very famous. Very famous, yeah. So again, are we good so far? Are we good so far? Yeah. I'll show you guys how to calculate. I'll show you guys. I can feel that you guys want to know exactly how to calculate, right? Type here for me if you want to know exactly how to calculate the control limits. Type here for me. Yeah, type here. Yes, I want to know. I want to know. And just before I show you guys how to calculate, just keep in mind that Shuhert presented few rules to check if your process is in control or out of control. And the very first rule is one data point above control limit, yeah, or below lower control limit, above upper control limit or below lower control limit, at least one. So if we have a situation, for example, like that, at 11 a.m. I went there to take my cheese bread, and then this specific cheese bread that was selected randomly, he was crispy on a level 30, on a level 30. So if I have a situation like this, see, it is flagged as a red little square, or a red dot. So it says that there is something special, something different, that must be checked. So just keep in mind that the very first rule, and maybe the most important rule, when you have one data point above control limits and one data point below the lower control limit, above upper control limit or below lower control limit. So see, let me show how can we calculate these control limits, and for that I'm gonna open up Excel. And I'm gonna show one of the most common mistakes, that people make when they are trying to calculate upper control limit and lower control limit. So many people think because of the 3 standard deviations to one side and 3 standard deviations to another side, many people think that it's just a matter of taking the data points, yeah? So let me take the data points, Control C, and then let me just calculate the standard deviation, you know, of the population or of the sample. So standard deviation of the sample of these guys here, you know. And you can do either using the standard deviation of the sample, because if you are a little bit into stats, you know that there is a difference between standard deviation of the sample standard deviation and population standard deviation. There is a difference in the denominator, yeah, because one considers the degrees of freedom, so n minus 1 and population no, yeah. So you can do and population no p, and we'll do with both, yeah. So here, because the denominator will be 9, yes. The standard deviation is the square root of the summation of each data point minus mean power 2 divided by n minus 1, and here the same thing but divided by n. So here, because the denominator is 10, yeah, this number will be lower than this number here, yeah. But then if you take like lower control limit, upper control limit, if you take 10, right, the mean, minus 3 times this guy here, 7.87, you see that it does not match. It doesn't match, yeah. It's close, but it's not the same. So we are trying to understand how to find this 7.636, and we just found out that it's not using the standard deviation, the sample standard deviation, right? Sample standard deviation. It is not. So maybe it's the population, and I have to tell you that it is not. It is not, but let's calculate here. Let's put so if you take mean, yes, minus 3 times standard deviation of the population, see, 7.98. It is not. So Minitab calculated, Minitab lower control limit is equal to 7.636, yeah. And then the key message here is we must use standard deviation of the real population, because here it's not exactly the population. It's not. Yeah, the population is really the standard deviation of the 1,000 cheese breads. I should have that number. So So the point is we must estimate standard deviation. We must estimate. Yeah? And we do that based on the famous and beautiful concept of MR, moving range. Yeah? Moving range will be very important to us. By the way, the mean of moving ranges, because see that I have here different moving ranges. And what's a moving range? This guy here, 1, is nothing but this guy minus this guy. 1, this guy minus this guy, always positive. Always positive. It's range. So max minus mean. Yeah, so this guy minus this guy would be minus 1. But then we always take the positive value, yeah, in module, right? The difference is 1. Here the difference is a little bit, it's 0.5. Here the difference is 1. Here the difference is 0.5. Yeah? Here the difference is 1, 1, 1. So the moving range mean, yeah? So the moving range mean is 0.889. Please let me know if you are following me so far. The moving range mean is 0.889. And we will need this information, okay? The moving range mean, or the mean of the moving range bar, yeah? Moving range bar is equal to 0, oops, see, 0.889, yeah? Zero point eight eight nine. Yeah. Well, we are looking for the estimation of standard deviation of the population, the real population. Yes, not the formula, the formula of standard deviation of the population applied to a mean. No. I want to estimate the real standard deviation of the population of all data points. Yeah, and for that I need the moving range bar. I will need the moving range bar and also a constant. Yeah, normally I do not talk about this, just to prioritize, just to give maximum love to the audience, to the people that are seeing this, having contact with this for the very first time. So mainly if you are having your very first contact with control chart, please let me know here in the chat if so far you are having fun. Type yes for me if so far you are having fun, because I'll need to go a little bit more technical, but I want to know if you are having fun. Yeah, it's important to have fun, because one of the most beautiful contributions from Shuhert was the concept of unbiased constants. It's a set, it's a list of constants. Yeah, it's a set, it's a list of constants that you will be using, again to estimate your standard, the standard deviation of the population. And let me show you where can you find. This is another thing that you can Google. If you just Google Shuhert or unbiased constants or control charts, unbiased constants, you will find them all. Yeah, but there are different constants depending on the control chart that you are using. For this control chart, where you have one data point, individual data points, you will need the D2. But let me show you why or where can you find these. Okay, every time that you run an analysis or you use a tool in Minitab, you will find here at the bottom left corner a help. Almost always you'll find a help. If you click here, you will be directed to a help web page, right? In this help web page, let me change to my language here, to your language. Yeah, let me change to English. You will be amazed to see the number of wonderful and powerful things. For example, theory. For example, example. Yes. For example, the formulas, methods and formulas. So if you want to know how to calculate control limits, yeah, then you can see that. Interesting. Lower control limit is mu. Mu is not x bar. But a good estimation of mu is x bar. This is funny, right? So if you want to estimate population mean, normally, if you took care of the basic sampling pillars, mainly guaranteeing that your sample is random, sample must be random, reliable, contextual, sufficient, yeah, mainly that, you can estimate mu by x bar, yeah, minus k times sigma. Sigma is the standard deviation of the population, not S. Yeah, as you can see, k, the default. Let me just change to this. The default for k is 3. Yeah, 3 times. So again, mean minus 3 times standard deviation. But now the thing is, how can I estimate sigma? So one of the ways to estimate sigma is by the moving range bar divided by D2. Yeah? But then D2, there is a table here. And D2 is a function of, yeah, you must indicate in this case the length of the moving range, because remember, I was taking one data point minus the other. So the length is 2. I could take, I don't know, 4 data points ahead minus the original. Then I can change this length. So the standard normally is 2, and in our case we have used 2. So we need to find the D2 for for, in this case, a W equals to 2. Yeah, so let's take a look. Let's find here what is the 2 equals to 2. Yeah, so it's 1.128. So please keep this in mind, 1.128. So let's go back, 1.128. Let's go back to Excel. Yeah. D2. In this case, D2 is equal to 1.128. Interesting. So if we want to estimate the standard deviation of the population, one potential estimation for the standard deviation of the population, yeah, so one potential way to estimate standard deviation of the population is simply taking the moving range, yes, moving range bar 0.889 divided by 1.128. So interesting, very interesting. So what Minitab is telling us, yeah, is that we can use as an estimator of the standard deviation, yeah, 0.788121, yeah. And once again, remember that we are trying to understand how did Minitab find this lower control limit, yes. So if we did this correctly, Minitab lower control limit will be defined as 10 minus 3 times this guy here. Yeah, and if you consider the 3 decimal places, I believe that at this point you have tears in your eyes. If you like stats, at this point in our class, I can feel tears of emotion in your eyes, because you were able to finally understand how does Minitab calculate, yeah, the lower control limit. And it's the same for upper control limit, in case you wanna know. Minitab upper control limit is equal to 10 plus 3 times this guy here, that once again came from the moving range bar divided by D2, right? How exciting is that? Come on, make some noise, So 12,364, let's see, 12,364, 12,364, yeah. No, it's my pleasure. It's my pleasure to be here with you guys. It helps me. To get better. Yeah, to get better. It's really exciting to be here. Yeah, please type here on a scale from 0 to 10. Guys, how to calculate control limits. It's a nerd experience, okay? I just followed this path because I felt here a nerd environment in a good sense. If you didn't get it, it's okay because software will calculate for us. Sometimes, not even in black belt classes, I teach exactly like step by step how to calculate the control limits. Normally, I don't do that. Only on official Minitab trainings. But I did that just because I felt a nerd environment. So again, it's just to have fun, This is, how do I say, to know how to calculate a control limit or not will not necessarily make you a better or a good or a bad belt. It's not because you know how to calculate a control limit in Minitab that you will necessarily be an amazing belt. No, it's good to know, but it's more of a nerd of a nerd moment. Yes, what I want you to know is control chart. It's part of statistical process control. Control chart, mandatorily you must work with sample. So please do not use control chart if you have population data. Yes. Another thing, you wanna say if this process is stable or not. So at this point, control charts, we are not talking about specification limits. This is capability analysis. This is another conversation. Yes. And if you have at least one data point above upper control limit or below lower control limit, at least one data point, your process is said to be out of control. Yes, out of control. Are we good? Yes, Gideon. I'll keep this here in YouTube. It's an open session. It's an open masterclass. Yeah, so it will be here in our YouTube channel. Yeah, so you'll be able to access later if you want. Yeah, I have just one more point to show you guys. Just one more point. This is measure phase. Yeah, this is measure phase. One of the most powerful features in a control chart is you can plot what we call control charts in stages. So the most famous, let's say, type of control chart in stages is the before and after. So you can have in your measure phase, this kind of performance. And then let's suppose our customer wants to have to increase, I want your cheese bread to be a little bit more crispy. Okay, wonderful. So we ran a continuous improvement project, and now we have 12, 12.2, 11.8, we have something like that. And we were able to collect again on another day, post improvement, one sample per hour, and we got that. Random samples, and same thing, yes. Then you will have a picture like that. This is one of the most beautiful pictures. because then you can clearly see that from 10 we see from 10, oops, from 10 we shifted our process to 12, yeah, and on top of improving the mean, what happened? On top of improving the average, what happened here? Thank you, Cesario. Thank you. Thank you, Monashi. Jennifer. Yes, Charles. Yeah. If you follow like step by step, it is easy. It is easy. I'm glad to know you guys like it. Yes, John. You are right, John. You are right. The variation has reduced, right? John Critkits. Yes. Yeah, and as a consequence, the moving range bar has reduced. Yes. So now my process is operating on a better level. It is also in control. We can say that before it was in control as well, but the variation has reduced. Yes. So it's more precise, It is predictable. It is predictable as it was before, but now it's predictable in a much shorter range, yeah, in a much smaller range, and this is good. This is good, yeah. Control chart. Did you guys like it? Yeah, did you guys like it? How much fun? How much fun did you have? Yeah. Tighter, yes, tighter UCL and LCL. Yeah. And normally when we have tighter, normally when we have, for example, when we have confidence intervals that are, kind of tighter as well, we express this saying that we gained in precision, yeah, in precision. We like to improve precision, statistical precision, yeah. Wonderful, excellent, guys. Even knowing I am not in my best condition, I hope you guys like it. Yes, right now, yesterday I was kind of strange. I got a fever and everything. Now I don't have a fever anymore, so I can see that my process is getting better. So I hope you guys enjoyed. Thank you so much for all of you that came in live to this session. Yes, and if you are watching this session recorded, um, it's okay too. It's okay too. It's always better. It's always better to join live, right? Because then we can interact. I can see John. I can see Shigemezu. I can see Aline. I can see Charles. I can see Abraham. I can address their questions. Vindra. Thank you, Vindra. You had fun, right? Cesario, yeah, Ray, Adronic. So if you are watching this live recorded, try to come at some day on a live session. Yes, guys, thank you so much. Thank you, Irvin. Yes, I am almost there. Almost there. Thank you so much. Bye bye, Marlon. Bye bye, guys. Have an amazing week ahead. Okay. Bye bye.